In this VibroMap application example, we will take a look at two thin, polymer-coated, single-stack piezoelectric transducers from two different production batches side by side. Our client Norbit wanted to know if the production process at their production facility had improved, and if so, we should see a difference in performance between the older sample at the top and the newer sample at the bottom. First, we run both samples through our patented damage detection scan routine. At first glance, we can't really say that one sample is better than the other here, but as the damage detection scan will pick up any delamination in the entire transducer stack, we should be careful drawing any conclusions just from these two images. Next, we will look at the actual performance of the transducers. We start off by looking at two lower frequencies. The first one is at 140 kHz, and we definitely see a distinct difference between the samples here. The movement out of the plane is much stronger in the newer sample, which is promising. However, we also observe that there seems to be a larger delamination somewhere in the new sample compared to the older one. This is also observed at 475 kHz. We see both more and larger areas of delamination here. It is also interesting to note that the overall movements are at a much more similar scale at this frequency. This is interesting, but let's have a look at the performance around the operating frequency at 3.7 MHz, which is after all the important part. At 3.2 MHz, we see that the newer sample moves like a piston, as it should. But the older sample has a very different and much less efficient behavior. It seems to have a more sinusoidal movement across the length of the transducer. Here we see that we also pick up minor details on the surface of the transducer, but these are apparently not related to the overall movement of the transducer itself. They are possibly related to bulk waves associated with small-scale structures somewhere inside the transducer. Though as we don't really know how the transducer is produced, this is only a hypothesis. When we go up to 4.2 MHz, we see something of the same on the newer sample, but to a much smaller degree. On the older sample, things are even worse here. There's now an additional diagonal movement in place. Also, in both these cases, the newer sample moves much more in and out of the plane than the older one. Finally, at the actual operating frequency of 3.7 MHz, the difference is very clear. The new sample behaves as expected, with a clear piston-like movement in and out of the plane, which seems to be rather unaffected by the delamination we saw at lower frequencies. The older sample has a much less efficient, wave-like behavior, and we also see large local movements related to the delamination found earlier. If you're curious about what more our instruments can do, please don't hesitate to get in touch.